Hello, this is Bart Stevens, and welcome to this presentation where I'll be helping you choosing the right root of trust in your next silicon design. So let me tell you first about what is a root of trust. Root of trust is a term that is overly used a lot in specific contexts, in different contexts. And for us here in the security world, a root of trust is the security foundation in a semiconductor or electronic system. What means that any security function, everything that happens in a chip that relies on securities or identities or secrets, basically rely on that root of trust, partly on that root of trust or completely. And since a root of trust typically is based in hardware, that root of trust can handle cryptographic functions, it can store cryptographic keys, and is also typically part of the complete booting process of the whole SoC where the root of trust is part of, so that you can also expect a foundation of the software chain of trust as the function of that root of trust. Typically, root of trust are designed to be in silicon, and going forward, as we've seen a migration from trying to build that root of trust in the main CPU, typically these days you see a need that this root of trust should be outside that CPU. CPU complexity is growing, which means that security vulnerabilities are growing in possibility. They actually are showing up. You may have seen in 2018 this meltdown, the Spectre foreshadow attacks, which were all based on flaws in CPUs that were actually built to increase performance and efficiency and capabilities of CPUs. We'll also talk a bit about Rambus's different root of trusts, the architecture, capabilities, and places and functions in the system. Now we know what a root of trust is. Why would somebody need a root of trust? And first, let's look at the protection requirements. Typically, we know that a device, it needs certain properties that it can trust. And these properties should be unsubvertible beyond capabilities of any reasonable attack scenario. And the reason I'm saying this, that for every design we and our customers build, it's always talking about what is the threat model? Who do we expect to attack? Who's benefiting from it? Because that defines that attack scenario. Is the attacker capable of looking at the board, at the PCB level of a design? Or is it just capable of looking at ports of a design because there is tamper detection in the system? Or can an adversary actually open the chip and see what's going on there? So that's, again, where you have these different threat models. In a root of trust, in a device, you can see many roots of trust, and they typically could also have different purposes. So one thing is immutability of the chip hardware and the ROM code itself. That already provides a trust foundation. ROM code, unchangeable, chip hardware unchangeable. So you can actually trust that the design that you built and put in hardware is actually doing what you want it to do. Chip and device unique IDs, public keys used to authenticate next firmware, and all kinds of other implementations or assets could be part of that root of trust. So root of trust is not necessarily a piece of OTP hiding a key. It's not that ROM code. It's the combination of all those implementation details that built the complete root of trust, if you will. And very important, immutability. So hardware design built in silicon, protected in silicon, that's what you need to build trustworthiness into a device. As already said, in many cases, giving a root of trust that may particularly be trustworthy under one attack scenario but it actually may use that property in a more advanced attack scenario. So at the end of the day, it's basically how much can a customer of ours, how much can your customer actually allow to spend on a root of trust? That means that could be in area, could be in performance, could be in power, could be in production cost. All those matters are important aspects. A couple of more aspects on why a root of trust is that aspect of providing the security foundation. So as said, in most scenarios, the most basic root of trust, the one of hardware immutability, it comes from the fact that functionality in silicon is hard to change. Root of trust products leverage various root of trusts available in silicon, and they use them in a secure way to offer security services to that SoC and to the applications running on the SoC, where we expect that the rest of the SoC that's outside the realm of the root of trust should not worry about the security and the protection of its assets, because it could rely, or it can rely on a root of trust enclave inside the silicon. So on top of that, in many cases, these root of trust products can even provide protection for, or at the minimum detection of, attacks against the silicon root of trust itself and against the security architecture protecting those services. Think of the root of trust handling keys. But if in that case the root of trust itself can be attacked, then those keys are still unprotected, and thus the security of the device cannot be guaranteed. So in this way, root of trust products, as we present them here, provide the trusted foundation that the SoC and the applications can use to build their own protection. So start with embedding a root of trust and rely and trust that root of trust to hold your keys and assets so you can build your security foundation in a proper way. Root of trust also provides, once it's deeply and profoundly embedded into the security system, it provides security and crypto services. As already said, it provides trusted foundation that SoCs and applications can use to build their own protection. And the root of trust products are expected to provide robust security and robust crypto service to that SoC and its applications. So this graph here, which is very simplified in the green, shows the general purpose processing subsystem. The CPUs could be GPUs, video processing, the whole application implementation of a device. And then in the blue, that's that secure processing block, that hardware root of trust. That comes typically for embedding into your design as a Verilog RTL product. And on the right, I listed here a list of secure functionalities that you could expect from a root of trust. You might not necessarily need all of them, but at the minimum, you need a couple. You can expect a root of trust to take care of securely booting itself, if it's programmable. You definitely should expect that the root of trust would help securely boot the SoC CPU's firmware. Same for firmware update, authentication of applications, attestation of the system itself in regular time intervals. Simple application use cases like secure data storage and secure key storage can be handled by that root of trust. Depending on your system, you could have on-chip non-volatile memory that is shared, and assets could be written and stored and maintained and kept in there in an encrypted way under a device unique key. A device unique key needs device personalization. How can you inject a secret device ID and a public device ID into silicon if you don't have the way to do this in yourself securely? You might use untrusted fabrication and assembly and test facilities. Can you expect these facilities to handle your keys in a secure way? With a root of trust, with a proper provisioning system, you can actually do this in a secure way at untrusted locations. The list goes on for quite some use cases. Device lifecycle management, having privilege levels in the programmability, multi-tenancy, which means that basically you as the device manufacturer could want to own a particular root key tree, but your customers would expect to have their own key tree that you have no visibility on. You might not want the responsibility of having knowledge of the device ID and want to hand it over to your customers, but they want to hand it over to their customers, which may be the service providers. Maintaining user data privacy, supporting secure communication, running runtime integrity checking of the system, providing simple things as cryptographic acceleration, while the security implementations and the crypto algorithms are already in there. That's all part of these root of trusts. Secure protocol implementations, secure debug, a very important one. Debugging today is something that's only allowed typically in engineering samples. Then once a device goes into mass production, e-fuses are typically used to disable debug, which makes RMA and in-field debug quite difficult. Having secure debug handled and managed in a secure way by a root of trust allows you to have in-field debugging at various levels. So quite some secure functionalities that you could expect from your root of trusts. So how do you choose then which one to embed in your design? Because there are so many choices and so many differences. What secure protocols do you want or do you need to support? Do you need secure processing inside that root of trust? Or do you have a closed system where there is no software loadability like in an Android environment where you can have apps from the App Store downloaded and executed by a user? Does size matter and power matter? And typically it always matters, but you can imagine that in battery powered devices or IoT endpoints, size and power matter more than in server-side or cloud implementations. Which geographies do you need to support? That means which crypto algorithms do you need to have supported? How do you want these crypto algorithms to run? Do you expect to need anti-tamper? Do you expect to need side channel protection of your cryptographic operations where keys could leak, bit values of keys could be leaked through power or electromagnetic measurements? And these are well-known techniques that adversaries are capable of using. How much performance do you need? Do you need programmability? And many other questions would need to be answered, and we would be happy in helping you answer those and choosing the right root of trust. So what kind of questions do you expect us to ask to you, or should you ask yourself in architecturing your chip, in dealing with your customer? Simple questions like, what's the end use of the chip? Where does it end? Does the root of trust need to manage your system? Who are you actually protecting against? What is the threat model? What are you protecting? Those are very important questions which can lead to a proper selection of root of trust. What happens if a compromised device, or if a device gets compromised? What's the risk here? Is it business value? Is it human value? Think of safety in automotive and security there. Is it just regulatory? Are there government fines involved if you don't comply? Or is it a matter of protecting intellectual property, protecting content or services? Think of set-top boxes, think of payment implementations. Is the reputation damage of your brand? Is it your risk that you're protecting, or is it your customer's risk? Where do you see added value? Another important question in order to choose properly is, where does device security versus cost versus performer rank in the priority of the design? We already passed the mechanisms that security is an afterthought. We already have now very good examples where security is designed in the architectural phase where it should never be an afterthought, but still there are these trade-offs. And will the root of trust augment existing security architectures? Is already something present that you want to build upon, that you need compatibility over? Or is the primary hardware security mechanism? Will you want to adjust the behavior of this root of trust in the field over time? Typically, hardware, ROM, as discussed before, that's immutable. But what if root of trust vendors found a way to still have flexibility in the field? That would be very valuable. And then finally, what do you want to implement custom protocols that are only visible to the root of trust? That means maybe you have a proprietary protocol, you have a legacy protocol, you want to go to different geographies, maybe typically in Asia, where you could expect the different algorithms to be used. Maybe you want to have the flexibility to have different SKUs there. Do you need your device certified to some security standard? Does your customer expect you to do this? Do you expect your customer to be able to do this? And then what kind of certification? There is NIST FIPS, typically used as a guideline for US government customers, where NIST provides prescribed algorithms, prescribed test vectors, you need to comply. There's common criteria, which comes from the mobile, secure element, and the payment world. CSIP as a new certification standard for IoT devices. ASIL, safety integrity levels for automotive. So quite some questionnaire here for you to answer that obviously we at Rambus Security are happy to assist. So let's dive a bit into what Rambus Security can bring to the table. How can we help you choose that proper root of trust? For starters, we have designed two implementation solution families, if you will. On the green on the left, we have a brand that we call Vault IP, which we marked as Secure Services and Key Manager. It's a root of trust design that you can embed in your silicon. And on the right here in the blue, there is the Crypto Manager root of trust family, which is a system security manager. And without boring you with all the details of this list, what I try to do here is do a left to right, line by line comparison and help you understand. So for starters, maybe we can say that the Vault IP is a family of small root of trust solution, typically targeting IoT, industrial, gateway, edges, clients. You could translate that into it's a very powerful but small and using quite some little amount of power for your root of trust. Definitely capable of doing all the crypto services you need. Where on the right side, it's based on a powerful, securely built Secure RISC-V programmable RT cores. They are targeting cloud, AI, and ML accelerators, FPGA designs, automotive designs, defense, and general semiconductors. It's a secure execution environment where you can have customer-written, customer-authored, and authenticated secure applications. When we switch to the left, it's a closed security environment with a built-in sequencer. Still, the Vault IP does secure boot assist for the host CPU as well as itself. It allows you to handle secure debug. It does secure key management, key storage, and use. It has a complete set of powerful random number generators, crypto accelerators, and it's FIPS 140-2 level 2 CMV certified. If you go to the right, same list happens, but subtle differences. Here you can see the powerful capabilities of a programmable solution. It's a secure boot manager for the complete SoC, for the RISC-V itself, that's the security processor, as well as the external host CPUs. There is secure debug, device lifecycle, and feature management. Secure key generation, where you on the left you see secure key management. Assume that it's a client device, that keys are generated somewhere else, typically in HSMs, in the provisioning ecosystem. Still on the right, same set, of powerful random number generator crypto accelerators, and FIPS 140-2 level 2 CMVP compliant. And then there are a couple of different configuration that we can choose. On the left, there is Chinese cryptographic algorithms versions. There are SSL TLS specific versions, very valuable for IoT, which are typically HTTP connected devices, IP connected devices. Specific configuration for low power IoT clients. On the right, Crypto Manager has specific configuration with ASIL-B and ASIL-D safety integrity levels as described in ISO 26262 certificates for automotive. There are specific configurations for FPGAs, which not means that we use the logic and map it efficiently in FPGAs, but we also overcome limitations where FPGAs cannot really offer good, solid, secure root of trust solutions in the soft logic, because you miss the aspects of having access to OTP secure memory, which a root of trust typically relies on. So we have a specific configuration where you can actually still use the FPGA soft logic, don't rely on the OTP, but can use external flash in a secure way. On top of that, the Crypto Manager also offers specific configurations with differential power analysis resistance, with fault injection attack resistance, which is the next level of protecting a root of trust. So all in all, two quite distinct root of trust families that, as a helicopter view, left to right has small footprint, low power, fixed function. On the right hand is powerful, programmable, in the field upgradable. They have the same set of powerful crypto accelerators. They are both FIPS 140-2 level CMVP, but there are definitely differences in security levels, in applicability, for example, on the DPA defaults and the certifications. So this slide shows then the actual predefined and pre-packaged configurations that Rambus security can bring to the table for fulfilling your root of trust requirements. Again, in the green, to be keeping the consistency in colors, is default IP family comprising of a low power IoT client, an industrial edge version, a specific version targeting China, not necessarily Chinese customers, but customers that want to see their products also be accepted in China with the OSCCA certification, and a specific gateway version with TLS implementations, including the more modern Poly, Cha-Cha, and Edwards Curve 25519 as examples. Those are existing pre-packaged, pre-validated, and FIPS certified solutions for IoT. And in the blue, there is a family of distinct configuration and implementations of the Crypto Manager, ranging from cloud to automotive to specific government implementations, increasing also the attack protection and for a larger attack surface. And then on the bottom, we have these two specific implementations for FPGA. And what you see in the part numbering is a bit automotive is a distinct implementation where you have basically detection for single event upsets. What happens if a glitch happens in a device, which is not necessarily a security attack, but it's something that happens in the silicon that needs to be flagged, because automotive is all about safety and should be protecting lives, if you will. Where on the 660 series, that's where differential power analysis, fault injection, attack analysis, as well as stronger security levels are protected. So there is a root of trust choice that will really fit your design, available in the Rambus root of trust catalog. In conclusion, let's wrap this up. We know that CPUs are vulnerable. All these complex microarchitectural features that are added for performance, they have created and shown and revealed severe security vulnerabilities. You should not trust to run your valuable security application you should not trust the CPUs by protecting your assets. Do build in a solid root of trust design. How do you do that? By isolating and siloing. The correct approach here is to protect against current known vulnerabilities, but also against future vulnerabilities, is to silo secure processing from general purpose processing so that you move them into a physically isolated domain as a root of trust. So what does Rambus do here? Rambus Security offers ideal root of trust solutions for chip security. We've shown the Vault IP securing IoT designs. There's the crypto managers securing cloud, automotive, AI, ML accelerators for protecting training models, training data, and AI inference algorithm implementations, and specific versions for defense, and all the other multi-tenant designs. So I would basically invite you to visit our web, to contact us if you need to know more, if you want to know more about this, if you want to help us choose the right root of trust for your design and reduce the time to market for your security implementation and increase the protection of your designs.